Hi, thanks for the invitation to the Samsung AI Forum. I'm very glad and the honor to be here. I'm Kyunghyun. I'm an associate professor of computer science and data science at New York University. Today, I'm going to share with you my recent work done together with the Nathan Ng, a PhD student at University of Toronto, and my collaborator Marjia Gassemi, who's a professor at University of Toronto as well. And it's called SIMBA, Self-Supervised Manifold-Based Data Augmentation. So we need to first talk about manifold assumption, which is at the core of data science, machine learning, and natural language processing. What manifold assumption is that the high dimensional data lie roughly on a low dimensional manifold. And then you can see how this assumption manifests itself in the real life by thinking of how digits that are written down by humans can only change in a very small number of ways. You cannot change the digit in any ways you want while keeping the identity as well as this digitness as it is. And then it was actively discussed by Yashua Bengio's technical report from 2009. Now, what is the science behind this manifold assumption? One way to view this manifold assumption and to use it in machine learning is to look at it from the view of the vicinal risk minimization, or VRM, that was introduced by Chappell, Weston, Botu, and Van Leek in 2001. In this VRM framework, unlike in empirical risk minimization, we're not only considering each and every training instance, but also a nearby neighborhood for each of those training instances. That is, we are not going to make the classifier work only on each data point that we observe, but also to behave smoothly around these labeled instances. And then in order to do so, we need to somehow define a local density estimate, which reflect the manifold structure behind data. And in order to use this VRM in practice, we have to, of course, use it in a stochastic gradient descent framework. And then in this stochastic gradient descent framework, VRM ends up being identical or very similar to data augmentation. For each mini batch, we have many training instances. And for each training instance within this mini batch, we are now going to add some noise, or we're going to sample another point from its neighborhood according to this local density estimate or the local manifold structure. And then we are going to take the sample neighbor instead of the original training instance as if this neighbor was the original training example. And then by computing the stochastic gradient using those augmented inputs instead of the original inputs, we get the stochastic gradient of this vicinal risk minimization. So what that means is that the data augmentation is equivalent to sampling from this local density estimate in vicinal risk minimization. Now, of course, in doing so, there are two questions that must be answered. First, what is this local density estimate Px prime of x? Or another way to put it is, what is this data manifold? And second question is, what should be the label of this newly sampled neighbor instance instead of the original label? Should we simply use the same label as it is? Or should we try to adjust the label according to the neighbor that we have sampled from this local density estimate? So let's talk about how people have been answering these two questions in different domains. And of course, the first domain that we often get to when we think about the machine learning algorithm is computer vision. And in computer vision, people have identified a priori what are necessary manifold structure, or at least a local manifold structure given any image. We know that any given image, such as handwritten digit or a picture of this teacup pig you see on the slides, we know that what are the kind of transformations that we can apply ourselves without changing the identity of an object within this image. For instance, in the paper by Alex Krzyzewski and others in 2012, which somehow some people have been saying that have has revolutionized the field of computer vision by introducing a very deep convolutional network. They use the horizontal vertical flips, random crops, and pixel intensity augmentation because they knew a priori that those are the transformation to which the identity of an object is invariant. Now, of course, people have been pushing this direction quite further. Last year, Kubuk et al. Have proposed that what we need to look into is not even to try to design these transformations ourselves as a machine learning researchers, but simply trying to go into those image manipulation toolkits. And in their case, they use the image magic toolkit and then just apply all possible transformations that have been implemented by the computer vision researchers and developers over the past decades. And then they called it RAND-augment, short for the random augmentation. Now, of course, computer vision is not only the domain that we're interested in. One domain that I'm particularly interested in is natural language processing. And last year, Wei and Zhou proposed so-called easy data augmentation, or EDA, where they simply said that we know that the words can be replaced randomly with a synonym, and generally the meaning of the sentence should not change. And also we know that we can always randomly insert some words or randomly swap some of the words or randomly dropping some words do not alter the meaning of the sentences too much. Because as you are hearing me, I'm making a lot of mistakes and inserting randomly the filler words. However, you are largely getting what I'm saying. So this is also a very domain-specific way to augment the data. And in this particular case, for natural language processing. Of course, we can be a bit more sophisticated. Already from 2017, people have realized that we can now use a new machine translation system, which have gotten so much better in recent years in order to generate many paraphrases of any given sentence or paragraph. And paraphrase here refers to another way to write the same given text without altering the meaning. And then how do we do that with the machine translation system? We're going to exploit the fact that machine translation systems are imperfect and machine translation is many-to-many mapping. So we're going to start from a given sentence, apply or to translate this into another language using machine translation system. And given that translation, we're going to use the reverse translation model in order to project it back into the original sentence, original language. And what we get is a paraphrase of the original sentence. And then this turned out to work quite well. And of course, what do you do if you don't know the domain, nor you're working with a domain where you don't really have any idea about this local density estimate or the local manifold structure? Already from 1991, people have realized that simply adding some unstructured noise, such as a Gaussian noise to the input, makes a neural network more robust to the small changes to the input, thereby making it generalize better to unseen examples. In fact, in 1996, Chris Bishop showed that adding some Gaussian noise to the input during training is largely equivalent to trying to make this neural net or the resulting neural net as smooth as possible. This is amazing in a sense that it does not require any domain knowledge, but is quite limited in a sense that we have to somehow cook up a noise distribution that we know how to sample easily from, and we know that that distribution makes sense in terms of the structure of the data. So then, of course, the question here is, can we in fact bridge this domain-specific data augmentation method and domain-agnostic data augmentation methods by learning this data manifold from often abundant amount of unlabeled examples? And then that's where the idea of denoising autoencoders comes in. In 2010, Pascal Vincent and others from University of Montreal proposed a very interesting way to train an autoencoder called denoising criterion. The idea is extremely simple. You train a neural net to denoise an artificially corrupted training instances. And this artificially corrupted instance is a very important idea here. we have already talked about it in the previous slide that and it's easy to generate or create a local density estimate from which we can sample a lot of the neighbors. It's unfortunate that we don't know that whether such an unstructured noise distribution reflects the data manifold or the local structures underlying this data. And what this denoising autoencoder does is to transform this unstructured noise distribution into a local density estimate from which we can sample and reflects the underlying data distribution. And how it does is to trying to figure out what is the direction in this high dimensional space that could be ignored. And that was 2010. Let's fast forward all the way to 2020. And nowadays, everyone in natural language processing, as well as even in computer vision, are psyched about the idea of so-called masked language model, which is represented by Elmo, Bert, and Roberta, which were all proposed and released publicly in 2018. And they have become de facto standard in natural language processing. A mainstream use of these masked language models, or BERTs, has been to fine-tune this pre-trained model for a downstream task. And then it turned out that a lot of problems that we believe are interesting and were difficult turned out to be very easily solved, even with a small amount of training instances, when we fine-tune this pre-trained masked language model. However, a few people have noticed how much these masked language models, when trained on a vast amount of unlabeled data, knew about the world in 2019. For instance, as you see on your presentation slide, BERT will be able to fill in some of the missing words. And then when you look at what kind of answers BERT, this masked language model, gives you, you notice that all those answers are all plausible. In other words, this BERT has learned what are the directions of the plausible answers of the plausible language in this high dimensional natural language space. And now you see where I'm getting it. And this is where we propose, I'm going to describe you what our proposal, that is SIMBA, self-supervised manifold based data augmentation is. Instead of using either the domain-specific augmentation nor the domain-agnostic augmentation, we propose here to use masked language model, or more generally, denoising autoencoder, as a way to sample from the domain-specific local density estimate without having to know about the transformations or the plausible transformations a priori. Because these denoising autoencoders will learn themselves what those local manifolds are, and then allow us to sample from it. So we start from some training set. For each training instance, we're going to apply the artificial corruption function and then feed that corrupted example into denoising autoencoder. And the denoising autoencoder is going to give us a reconstruction that is, in fact, a sample from the neighborhood of the original training instance. And then this sample is a sample from a distribution that reflects the underlying data manifold. And then we use that example instead of the original training instance. Now, where does the self-supervision comes in? Self-supervision comes in from the fact that we are not going to use we're not necessarily going to use the original label, but we're going to use the label provided by the original classifier or the previous classifier that was trained on the original clean data. So we are exploiting the fact that these classifiers tend to generalize to a small neighborhood in the data so that we can trust the labels predicted from this classifier as long as we're sampling from the nearby point centered at the training instance. And then these equations on the slide that you see are what I have just described to you in words. So since we don't really have much time, I'm not going to go into the detail. But what I wanted to point you out here was that effectively what we propose here is a modern form or the modern implementation of stochastic vicinal risk minimization that was proposed already in 2001. That was nearly 2 decades ago. Now, of course, the question is, how well does it work? So we tried this approach called Simba on many different problems. First problem that we tried it on was text classification. For text classification, we tried it on two different subtests. One is sentiment analysis, where we trained our model to look at a review of a product, such as movies or restaurants or actual products from Amazon, and then try to predict what was the star rating that reviewer gave. So that's a proxy to the sentiment of the reviewer at the time when reviewer was writing the review. The second subtask was natural language inference. This is a problem where we're given a pair of sentences. One sentence is premise and the other sentence is hypothesis. And then we want to know if one of them entails the other or one of them contradicts the other. Of course, there's the option that they may in fact be neutral with each other, and then this classifier needs to tell whether this pair of sentences belong to entailment, contradiction, or neutral categories. And then we tried it on two separate data sets as well. As baselines that we compare against, or the compare Simba against, we tried easy data augmentation that we talked about, unsupervised data augmentation we also talked about. This is based on the machine translation systems. And then we also tried the conditional birth contextual augmentation, which is quite similar to Simba in a way that it uses the mask language model, but the motivation and how it works differs significantly from the proposed Simba. So interesting thing about this data augmentation algorithm is that this is more of a meta algorithm in a sense that it doesn't really matter what kind of classifier you use or what kind of loss function you use as well. So we decided to try different underlying classifiers, including recurrent neural net using LSTM units, convolutional neural network, and the Roberta, which is one of the largest mask language models that we fine-tune. So as you can see from this slide, which is a bit dense, I can tell you that the proposed Simba works better than all the other augmentation approaches that we have compared to, as well. And also importantly, Simba never degrades over the baseline that was trained without any augmentation. This is an important point because the whole point of the augmentation procedure or the data augmentation is to ensure that the classifier is going to get better. But then if we don't know that it won't degrade the underlying classifier, it becomes effectively impossible to use in practice. And then this trend was clear across different categories of products that we have looked at, even in the case of the restaurant review. And the same thing we could observe from this natural language inference task as well. So what are the effects of setting different hyperparameters or knobs of this Simba? So what we have seen is that the improvements that we see from using Simba for data augmentation does not diminish even if we have a large amount of training instances. That's probably because the input space is so high dimensional. However many training instances we collect is never enough to cover the entire meaningful data manifold. And it turned out that it is really important to use as many neighborhood samples as possible, although it does converge relatively quickly. So in most of our experiments, we have used about 5 neighbor samples from the denoising autoencoder for each training instance. And it turned out that the quality of denoising autoencoder itself is not too important, although it is important to use a reasonable denoising autoencoder. And then finally, we wanted to also look at whether it is necessary to use this self-supervision. And it turned out, and perhaps as expected, that if you have a good classifier to start with, it does help to use self-supervision. Of course, classification is one thing, but classification is pretty dull. So we wanted to try it on the machine translation. In particular, we wanted to look at how Simba, this data augmentation technique that we have proposed, could help with the low resource machine translation. We looked at German to English translation with the high mismatch between the training and test domains. And also we looked at one of the most extreme case of the low resource machine translation, translating German into Romansh, which is a language that is spoken in Switzerland. And as a baseline, we tried a bunch of existing approaches. However, we did not compare it against an existing approach that uses a large-scale target-side monolingual corpus. That's because those approaches are simply complementary and orthogonal to what we propose in Simba. So in the future, what we would like to see is whether we can gain further in terms of the translation quality by using Simba together with, for instance, back translation. Similarly to what we have seen with the classification, what we have observed is that the Simba indeed works better than any of the existing baseline data augmentation algorithms that we have tried. And also, Simba never degrades over the baseline, which was not necessarily the case with the baselines that we have compared against. So to slowly wrap up, this kind of manifold-based data augmentation in hindsight looks so obvious and that we should have done a long time ago, but it's always easy to connect all these dots looking backward. And by looking backward, in my mind, I see this kind of connection or the network of the dots. So we already knew about the data augmentation and its utility from early 90s. And then we knew about the importance of the manifold assumption all along, but was very carefully formulated in 2006. And then denoising autoencoder was proposed already in 2008, largely based on the intuition of manifold assumption. While these things are happening, vicinal risk minimization was proposed largely independently in 2001. Now, what we know is that because we now see all these pictures or all these dots, we can now connect it, and then we end up with the Simba, which turned out to be one of the state-of-the-art approaches to data agnostic data augmentation. And then it works for classification as well as machine translation without the issue of degrading the quality of the baseline classifiers. So before I finish, I'd like to point out two possible future directions that I believe we should pursue so that we can make Simba even better and more broadly applicable. First is the robust optimization. So robust optimization is unlike the usual empirical risk minimization, where our goal was to maximize the accuracy on the average case. On the other hand, this robust optimization focuses on the worst case scenario. That is, we want to look at the worst possible perturbation to the input, local perturbation to the input that's going to make the loss go up as high as possible, and then trying to ensure that the loss on that worst case perturbation is going to be as low as possible. Now, this makes a lot of sense when we can solve this inner loop of finding the worst perturbation, except that it's really difficult to do so when we are working in a high dimensional discrete space. Now, if we knew or if we could use such a learned manifold structure from a denoising autoencoder, can we solve this inner loop approximately but much more efficiently in order to make the robust optimization much more feasible, and also thereby allowing us to build a classifier that's going to be more robust to the adversarial examples. Second direction I believe is really interesting is trying to go beyond this local augmentation. Most of the augmentation techniques that we have used in our community, including Simba I have just described you, relies on the local perturbation. So given a training instance, we're going to look at a nearby point. And we want, I believe, to go beyond a small local neighborhood. Unfortunately, I have absolutely no idea what to do about it, but nevertheless, it's interesting and I believe it's worth pursuing. And then that concludes my presentation. Thank you very much again for inviting me to the Samsung AI Forum. And that's it.